Ever wonder what powers your phone, your laptop, or your electric car? It's a liquid electrolyte lithium battery. But there's a new technology on the horizon that engineers are calling a game changer: the solid-state battery. Today, we're going to break down exactly what that is, why it's so exciting, and what challenges still stand between the lab and your daily life. Let's start with the basics. Every battery has three key parts: an anode, a cathode, and an electrolyte. Think of the anode and cathode as warehouses for lithium ions, which they store and release when you charge or use your device. The electrolyte is the highway that lets those ions travel between the two warehouses. But here is the crucial part. It also forces the electrons to take a different route through the external circuit, which is what powers your device. In the lithium-ion batteries we use today, that electrolyte is a liquid. It's usually a flammable organic solvent, kind of like a special salt water for lithium ions. This liquid works great, but it has a big downside. It can catch fire. A solid-state battery, as the name suggests, replaces that flammable liquid with a solid material. This could be a ceramic, a special type of glass, or even a polymer. It still lets the lithium ions pass through, but it's a solid highway instead of a liquid one. So, why go through all the trouble of swapping a liquid for a solid? The benefits are huge and fall into three main categories. First and foremost is safety. Since solid electrolytes aren't flammable like their liquid cousins, the risk of those dramatic battery fires you hear about is significantly reduced. No more thermal runaway from a punctured or shorted cell. That's a massive win. Second is energy density. This is the big one for electric vehicles. Solid electrolytes make it possible to use a pure lithium metal anode instead of the graphite we use now. A lithium metal anode can store way more energy in the same amount of space and weight. What does that mean for you? An electric car that could go much farther on a single charge, or a lighter car with the same range, making it more efficient. Third is longevity and performance. Many solid electrolytes are more stable over time. They don't suffer from the same degradation problems that slowly kill liquid-based batteries. This could mean a battery that lasts for many more charge cycles and performs better in extreme heat or cold. But if solid-state batteries are so great, why aren't we all using them already? Well, the road from the lab to mass production is paved with some serious technical hurdles. There are three big ones that researchers are wrestling with right now. The first challenge is ionic conductivity. The solid electrolyte needs to be a superhighway for lithium ions, letting them move just as fast as they do in a liquid. Many solid materials are more like a congested side street. They just don't conduct ions well enough at room temperature. Scientists have found some promising ceramic and glassy materials that are almost as good as liquids. But making them consistently and at a large scale is a major material science puzzle. The second is what engineers call the interface problem. Imagine trying to perfectly glue two solid objects together with no gaps. It's tough. When a solid electrolyte touches a solid electrode, tiny gaps or unwanted chemical reactions can form at that boundary. This creates resistance, which wastes energy and can even damage the battery. Solving this means designing materials that stay in perfect contact even as the battery expands and contracts during charging and discharging. And the third hurdle is manufacturing and cost. Our current battery factories are giant, multi-billion-dollar facilities optimized for making liquid electrolyte cells. Switching to solid-state often requires completely new equipment, different processes, and sometimes high-temperature steps that are slow and expensive. Even if a lab prototype works perfectly, Figuring out how to make millions of them affordably is a whole different ballgame. Now, not all solid-state batteries are the same. Researchers are exploring a few different paths. One approach uses ceramic electrolytes. These materials can have fantastic conductivity and are very stable, but they're also brittle, like a dinner plate. This makes it hard for them to handle the vibrations and shocks of being in a car. A second approach uses glass or glass-ceramic materials. These are a bit more flexible and forgiving than pure ceramics, which helps them maintain contact with the electrodes and handle volume changes better. A third route uses polymer electrolytes. Polymers are flexible and easy to manufacture, which is a huge advantage. The catch is that their conductivity at room temperature is often lower than ceramics. So, many polymer systems either need to run at higher temperatures or have special additives mixed in to help the ions flow. Many of the most promising designs are actually hybrids, combining a flexible polymer with ceramic particles to get the best of both worlds. Let's be realistic about performance. You'll hear headlines about solid-state batteries doubling EV range. In a controlled lab setting, small cells with lithium-metal anodes can indeed show massive gains in energy density. But a real-world battery pack also needs packaging, cooling systems, and safety electronics. By the time you add all that, the real-world improvement is smaller. So, the amazing numbers you see in scientific papers are not what you'll find in a production car for several years. And what about safety? Yes, removing the flammable liquid is a huge step forward. But solid-state batteries can have their own unique failure modes. For example, some sulfide-based ceramics can release toxic gas if they break. And if a brittle electrolyte cracks, it can allow tiny, needle-like lithium dendrites to grow through the crack, causing a short circuit. Engineers are working hard to design materials and structures that prevent these new risks. So, when can we expect to see them? Battery companies, automakers, and startups all over the world are pouring billions into this technology. But timelines often slip. Some companies are starting with hybrid designs, adding a thin, solid layer to an otherwise conventional battery. This offers some safety benefits without needing a complete factory overhaul. Others are going for the full solid-state holy grail. A realistic view suggests we'll see gradual adoption over the next decade, starting with niche applications. Think aerospace, military equipment, or specialized industrial tools, where the high cost is justified by the need for superior safety and energy density. Electric aircraft are another prime candidate, because every pound saved means more range or payload. For consumer electronics, like your phone, the cost is a huge factor, so full solid-state adoption might take longer. Finally, what should you keep an eye on in the coming years? First, look for announcements of pilot manufacturing lines and real-world vehicle demonstrations. That's the sign that lab success is translating to the real world. Second, watch for independent, third-party testing data on safety and cycle life, not just company press releases. And third, look for supply chain and manufacturing partnerships. When you see major battery companies signing deals to build factories for these new materials, you'll know the industry is getting serious about scale. To sum it all up, solid-state batteries are a genuinely exciting technology with the potential to make our devices safer and longer-lasting. They aren't one single thing, but a whole family of different approaches, each with its own pros and cons. The challenges are real, but the progress is steady. The race is no longer just about science in the lab. It's about engineering and manufacturing at a massive scale. If this breakdown was helpful, make sure to subscribe and hit that notification bell. In our next episode, we'll dive deeper into the specific materials and see which ones are closest to hitting the market. Until then, stay curious.